And I'm also starting the recording. Great. So we were talking about the data in inference. Okay, so we had talked about. All right, so all right, I will mute you. Okay, if you have any questions, feel free to ask. And do you have any questions related to what we have learned so far? Okay, so I think we were here somewhere. So we talked about relative frequencies, and then I think we had talked about all of this. Yeah, we were into here. All right. So we talked about. All right. I think we were here, right? So we had talked about the basics of probability. We have talked about other questions. So do you have any questions related to big data analytics so far? It'll be okay, completely okay. If you want me to explain a few things again, I will be more than happy. But the idea is to be very comfortable with whatever we have learned so far. Okay. If you want to go through.
Please,
Okay.
yeah, please open a chat window for me.
Okay. Okay. So chat window now. So you don't even see the questions window, right? You neither see the questions window nor chat window. Uh, and I think it's okay unless somebody else joins in. You can speak. If you are okay with your voice getting recorded, you can keep yourself unmuted. All right. I think Mehdi will be joining in 10-15 minutes. So all right. So he called up a few minutes back. All right. So, do you have any questions for me before we move forward? So, we have talked a great deal about various things in this. We talked about the ways of analyzing data by looking at the graph. If the graph is, so I'll just do a quick maybe from here because there are too many things which needed to be uh, which we should have gone through. Okay, so when we started statistical inference, we talked about the approaches, basically not to rely on anecdotal incidents. So November 30th class complete recording. Okay. I'm not sure who was the co-organizer that day. I think November 30th. This one. Part 1, Part 2. Okay, this is, I think, only up to, it's only for 2 minutes. And then we have basically lost around 40 minutes here, right? Okay, so do you know who was the co-organizer that day? I think he hasn't sent me the video so far. Okay. Yeah. So, okay, let me find out. Okay, let me find out. Let me make a note of it. Okay, so let me. All right. So to do for this course are number one, fix November 30th recording. Okay, so if you have an idea, as in, so we we talked about, what did we talk about? Okay, all right. I think, oh, we missed a very critical part actually. Oh, oh, actually, you can this. Did we talk about the Python here? Never mind. So I think I need to figure out where are those recordings, and then accordingly make it. Okay. Okay. So if you remember who was the organizer that time, co-organizer, who I promoted to be the organizer that day, then we can quickly ask him to give the recordings. Okay. All right. So I think we have Mehdi also. Hey Sahib, welcome to the session. Are you able to hear me clearly? All right. Great. Now, the question. All right. So we were about to go through again whatever we talked about statistical inference. So I'll just go like at 90 miles per hour. So we started with statistical inference. We talked about anecdotal inference and the actual inference. So the way we conduct the studies, the way we and the kind of while we talk about inference, the kind of variables we talk about, the example of various kinds of variable like continuous and non-continuous or discrete or numerical. Okay, and then we talked about the relationships, dependent and independent variables, and we also talked about positive and negative. Then we talked about sampling bias, what kind of sampling bias that could occur, then sampling methods. And after that, we talked about the when you design an experiment, what kind of things you keep in mind, and then various kind of terminologies for the experiment design. And afterwards, we talked about the sampling ways, and once we have sampling ways, we have the data, then we can continue to visualize the numeric data. To visualize the numeric data, the easiest one is scatter plot. These are scatter plots, and the scatter plots have the relationship like negative, positive, curved, linear, strong, weak, or what is the outliers. So while representing the data, we also talked about histogram. Histogram is nothing but on x-axis you have the buckets in certain increasing order. On the y-axis you have number of people or number of things that lie on that bucket. So it basically, histogram shows you the distribution of the things into various buckets. And afterwards we talked about the properties of this histogram, and in terms of modality and skewness. And then we also talked about examples of modality, and then we talked about something similar to scatter plot and histogram called dot plot. Okay. Then we talked about a very interesting representation called box plot. Okay. Box plot are statistically significant diagrams. They are small, but they give you a great idea about skewness and modality. They basically give you more idea about the skewness. Also, the we talked about something called intensity map to analyze data by looking at it, and then we talked about the other numeric ways of representing data or analyzing data. So one way of, first is gathering data, then analyzing data, and then analyzing data by looking at it or by looking at the numbers. Okay, so by looking at the numbers, we need a center of the point. So center could be mean, median, mode. Okay, and then we talked about mean, median, mode, and then we talked about the examples in terms of real data. Okay, So we try to visualize as well as draw the center and the spread across the various kinds of data. And so you can we talked about this the center in terms of the visualization, and then we moved ahead with respect to the spread. Okay, the other measure of the data. So one measure of the data is where is the center, other measure of the data is how it's spread. Okay, so we talked about standard deviation, how do you compute it, and keep this in mind, square of the difference is also statistically significant uh, as so standard deviation and squared of standard deviation both are statistically significant numbers. And we talked about variability versus diversity. And so we also talked about another number which defines the data other than mean, median, other than the center and the spread. We also talked about interquartile range. Interquartile range is also a way to measure the spreadness. Okay, so out of statistics, to understand a particular data, there were two kinds of statistics, robust and non-robust. We talked about it. And sometimes if you are trying to visualize or understand data, sometimes the data doesn't budge in so easily. So in those cases, you might have to do the transformations. And to do the transformation, if the data is heavily skewed, suddenly there are a million number, and then suddenly there are thousand, then there's 100, and so on. If you try to draw certain data, this kind of data, it's very difficult to fit in on the graph, and that's where we need transformations. So in such kind of data, you can try the transformations like log, okay, like a square root, or we could try inverse. All right, because if your x-axis graph is bigger than the y-axis, you could try doing the inverse, and you will get what values were there on the y towards the x. Okay, and sometimes you have to explore. So that was numeric data exploration. The histogram and all these kind of statistics is great for numeric variables, but sometimes you have these frequency tables and bar plots. Those are for category variables. Category as in you have each value does not have the number associated with it. It is basically a string or a caption or a bucket. So for that, you do a similar histogram by doing the frequency analysis. Okay, now bar plots and histogram, they look same, just that on x-axis in one there is a categorical variable, in another it is the numeric variable. Okay, so we have pie chart and species distribution here, just showing you that when you draw a pie chart on a categorical variable, it may not look very great. Okay, because you can see that here. Okay, so yeah, all right. Now next is relative frequency distribution. So when you have two categorical variables, one is say income and other is say difficulty in saving. These are the two questions people have answered. For one, they have said that their income was this much between to this to this, and second variable was this. And if you have to plot this kind of data on a graph, and you can also compute relative frequencies to figure out the correlation between two variables. Okay, so these are the relative frequencies. All right, is this relative frequencies chart clear to everyone, Sahib uh, and Anusha? All right, good. Okay, so I hope the relative this thing is clear. And next is a segmented bar plot. So segmented bar plots are a great way of doing the relative comparison. So you can see that less than 40K, this is the distribution of various not sure various difficulties of saving. So there are these many people say it's very difficult to save. These people say that it's somewhat difficult to save. And in this, there are these many people said that very difficult to save and somewhat difficult to save these many people. And so this way, relative frequencies can be visualized in this, or we could do the you could normalize the data to the scale of 1, meaning you can compare between these two but you cannot compare between these two. Okay, you can compare between these two. All right, so although you can see that this is you know 63% with respect to this, but the number was different here. See, it was like almost 50%. Here it's 80%. So if you want to compare between the two stratas of the society, then you don't do the relative, you do the actual, and then you can see, oh, these many people are varying. While if you want to just compare in the same income group, then you do the relative. All right. Now, plot is just another way of representation of the same data as this bar plot. It's the same as that one. All right, all right. So basically, it's a relative bar plot. All right. Now, side by side box plots are similar to what we had discussed earlier. That, so here, for the first year, some number is there. Okay, so I forgot what was the number here. All right, we also talked about this part. Now, we talked about a small case study where we talked about the numbers here, and we also started discussing the alternative hypothesis and this difference. All right, good. So we talked in general about inference. So the way we compute the inference by computing the probability of defendant being guilty or not, by comparing how much deviation is there in the defendant against the innocent. Okay, so against the alternative hypothesis and null hypothesis, we compare statistically what is the probability of alternative hypothesis, and then if the probability is really high, then we rule that. Okay, so let's just discuss the probability. We talked about probability in terms of it's a process. It's the chances of something happening. Okay, okay. So probability of something happening are chances that chances out of one. What is the chances of it happening out of one? It should be between 0 to 1. For example, you throw a coin. The chances of head is how much? Anybody? You throw a coin randomly, a non unbiased coin. So the chances of a coin becoming head is 1 by 2, right? That is 50%. So the way we represent in probability is as 0.5. Now, in long run, maybe when you throw it couple of times, maybe you end up with head, head, head. But in long run, if you keep on throwing it, you will always have equal number of heads and tails. If heads and tails are not equal in a long run, meaning say you throw it 10,000 times. If you throw it 10,000 times, if the heads and tails are not equal, occurrence is not equal, then we call that there is something wrong with the experiment. Maybe the coin is biased. Okay, so more observations will, in a long run, when there are more and more occurrences, the probability will be mostly the truth. Okay, unless the system is unbiased. All right, so that's how you look at the probability. All right, say you have a coin, you toss a coin 10 times and it lands on head each time. What do you think the chances that another head will come up on the next toss? Anybody? Anusha? Yes. So you tossed a coin 10 times and it lands on head each time. Now you are planning to toss it next time. What is the chance that another head will come up on the next toss? Anyone? Yes. So Sahib is saying less than zero point 0.5. And what is your opinion? Yes. Question is, question to you is, what happened in past? Does it impact the coin in any way? Does it impact our process in in the next toss in any way? So you could already toss 10 times and every time it was head. And we know for sure that it's an unbiased coin. Okay? So when you throw the next time, what are the chances of head? Zero point 0.5 or less than zero point 0.5 or equal to zero point 0.5? Less than, more than, or equal to? Anusha? All right. Does does the chances of coin, when you throw a coin, does it matter to the coin whether you have, how many times have you thrown it already? Does it matter to the coin? Or how many times somebody has already thrown it? Does it matter to it? Yeah. All right. All right. So it doesn't matter to the, yes, that's right, Anusha. So it doesn't matter to the coin. Yes. So Sahib's question point is, so in large number of observations, we assume that the probability will be zero point 0.5, and we already have H in the past. Okay. So, right, right. So yes. So this, I mean, we call it gambler's psychology. That just based on the past history, they think that the chances of head or tail had changed. Ideally, it hasn't. It hasn't. Okay? It hasn't. Chances are still the same. Because it doesn't matter to the coin whether what happened in past. Okay? So the chances are still the same. It takes some time to sink in. Okay? There are many more examples of such kind of thing. Probability is still 50%. Okay? Probability of head on the 11th toss or the 10th toss, it is the same thing. The coin is not due for a tail. This is something like the way we always think, just because somebody has has been having head, that means it is due for tail. No. Common misunderstanding of law of large numbers is the actual, you can see that. So, this is the common misunderstanding of law of large numbers. And yeah, so basically, it's a gambler's fallacy. It's a law of averages. Okay, so we need to understand the disjoint sets, but I would like to take one more example for you. All right, here is a very contradictory question, and this is something which I found very intriguing. In a village, for 1,000 years, the rule has been that they keep giving birth until they get a boy. If it's a girl, they have another baby and keep on doing that unless it's a boy. As soon as they have a boy, they don't have any more kids. Now, question to all of you is, what will be the ratio of males and females in this village now? It has been, this culture has been there for thousands of years. Say 100,000 years or 50,000 years or whatever. Anybody? What will be the ratio of males and females now? Or or people keep on throwing the coin or tossing the coin unless they have a head or tail. They have a head. If they get a tail, they throw it again, and so on. So question to all of you is, will the head and tail, total number of head and tails will be same, or head will be more than tail, or tail will be more than head? So, okay. On the same lines, in this village, do you think the ratio of males will be greater than females? Ratio of males will be less than females, or females will be equal to the males? Yes, Sahab? Anusha? One less than one, greater than one. Number of males divided by number of females, how much would it be? Sahab is saying that it'll be, females will be greater than males. Okay. I think yeah. Okay. Now finally, Sahab is suggesting that females and males will be equal. Alright. So Anusha is saying less than one, meaning Males will be less than female, or female will be less than males, or equal. Okay. So Anusha is saying that females will be less than greater than males. Okay. Okay. Why do you say so? Just because they keep on getting the baby as soon as they have a until they have a boy. All right. Now this is a very interesting question. This is a very interesting question. Now, the law of large numbers, if you think about it, it says that if you keep on doing something, no matter in what fashion, um, okay, whether you throw it three times today, three times tomorrow, and somebody throws it four times, so the coin will always have equal probability of head and tail, right? So if you do the computation, you will find out that it is actually ratio of males to female will be equal because so Anusha's question is in every female only one boy but one or more female. Yeah. So but if you think about it, there are equal chances of both. There are lots of people who have their first boy itself. There are another people. So there will be some people who have first as boy, right? So if you draw it, it's a very interesting question, and it takes some time to sink in. Okay, so let's say there were 100 people. Okay, there were 100 people. Okay, and they have the baby. So they will be uh, how many boys? 50 boys and 50 girls, right? 50 girls. I'll just make it blue. 50 50 boys. So this is uh, girls and boys, right? So right now, as of today, both are equal, correct? Now, the guys who had these families who had the girls, they will go for another round, and then they'll have all of them, uh, these these families, the 50 people, they will have again the kid. Now, out of them, out of these 50 people, how many girls and how many boys will be there? How many girls and how many boys? 25, 25 girls, and I changed the color. Okay, and 25 boys. See that? Now again, these people will go for another, the another round, and if you see it, okay, so they'll have something like say 12.5. I'm just putting the decimal number so that if there are we are talk computing out of 100, right? If there are millions of people, so you can see at every stage the number is same. If you see, these are the girls and these are the boys. Do I make sense, Sahib was anyway convinced that they'll be equal. Anusha? So out of 100 families, 50 had girls and 50 had boys. Therefore, 50 girls, 50 boys, right? Out of 50, again, these 50 families who had girl, they went for another round, and then 25 had girl and 25 will have boy, right? Anyway, there are equal number of people. Make sense? Was he able to clear it? All right, all right. So, so that's why you need to keep in mind what does it mean by disjoint or independent probability than the dependent one. Okay, it doesn't matter. The probability of a girl or boy does not change if people create whatever strategy they want to do. Okay, if one comes up another with another strategy saying all those people who have two girls will not have will should not have an sorry, people should stop as soon as they get two girls. Okay, no matter what strategy they people make, as long as they do not interfere with the probability, okay, as long as they do not cheat, it will be equal. Okay, unless somebody is going for something like a ultrasound and then killing the baby, so that will be like disaster, and in only those cases it will be disbalanced. In this way, whatever strategy people have, it won't impact the total occurrence of the it won't impact the ratio of male to female. Okay, it took me some time to first get the sense of the natural events. It took me fair amount of time, unless I did this calculation which you saw just now. Unless I sat down and did this calculation, I did not realize that they will be equal. Okay, it always felt that people are impacting the overall probability. All right, but in fact, if you just do, even if without calculation, if you can think about what is the chance of a girl or a boy if somebody had already a girl or a boy, if it's one, if there is no biological proof that it impacts, then we are good and it should be. So biologically, it is proven that no matter how many kids or no matter whether it was a boy or girl, the probability is same. Let's say this is biological proof. Now, it doesn't matter how many kids people have, therefore it will be equal. Okay, therefore the two will be equal. All right. Now, so so that we need to understand what does it mean by disjoint sets, because we will the Bayesian inference depends on understanding non-disjoint and disjoint sets. Okay, so disjoint event means both cannot happen at the same time, meaning throwing a coin cannot result throwing a coin cannot result head and tail at the same time. If somebody asks, when I throw the coin, what are the chances that I will get head and a tail in a single shot? Okay, what are the chances of A and B happening at the same time? So that's not possible. Therefore, the probability of A and B is zero. Similarly, what is the probability that a student will fail as well as pass? The probability is zero. And this whole mechanism gets complex when you have more and more relations. Okay, you will see it as we go forward. Now, non-disjoint set is can happen at the same time. The two events can happen at the same time, or the relation between A and B can exist. So, for example, what are the chances that a student get A in statistics as well as A in economics, right? While a student cannot get A and B in statistics, he can only get A and A in statistics. He cannot get both A and B, right? A or A plus in statistics. Okay, but we can always say that this student got some some A or some other score in statistics and economics in the same semester. So these are non-disjoint events. These can happen, both of these could happen at the same time. All right. So just a second. All right. So here you could also define something called mutual exclusive. We'll talk about it in a minute. So the other is the chances of probability of occurring A or B. Okay, so generally the chances of A or B, as in what are the chances of student passing in statistics or passing in economics. Okay, is generally equal to chances of student passing in economics plus the chances of student passing in the statistics minus chances of student passing in both. Okay, so that's how we generally compute the OR relationship. Okay, so that's a union of total number of sets. So out of 100, if these many students are passing in A, these many students are passing in B, these many students are passing in both, then this whole colored region means in either, right? And that is why we are subtracting the A and B. Why? Because that region has been counted twice. When we said A plus B, this region got counted twice, therefore we are subtracting it once so that we only get this shape. Alright? Now, if A and B are two disjoint sets like this one, then we can always sum it up and therefore we get things like this. All right. So let's say I'll ask you a question. So question is what is the probability of getting 1 or 2 on a dice? Anybody? You throw a dice. Dice has 6 faces. Okay. Anusha. So probability of 1 is how much? 1 by 6. And probability of 2, as in when you probability of getting 2 is 1 out of 6. Probability of 1 and 2 is 0 because it can never happen that 1 and 2 both can come. It'll be only 1. Therefore, probability of 1 or 2 is 1 by 6 plus 1 by 6, 1 by 6 plus 1 by 6 minus 0. And therefore, it'll be 1 by 3. Great, Sahib. Thank you. All right. So that is correct. All right. So whenever we are counting or whenever we are computing probability, we do something called sample space. We first figure out what is the sample space. That is kind of a union set, a set which contains all possibilities. Okay. The sample space of is a collection of all possible outcomes of a trial. For example, two coin toss could result in head-head, head-tail, tail-head, and tail-tail. And first, computing the sample space is something which is very important in case of probability. And in case you don't have a great hand at the probability, the first thing you need to do always is compute the sample space. What are the possibilities? What are the all possibilities? And then you pick up out of that, you count what is the possibility which we are computing the probability for. For example, what is the possibility that you throw the coin, you throw two coins, and both of them get the same side? Okay, both of them either get head or head tail. What is the probability of that? Anybody? So the whole thing about probability is counting. You just have to count the whole sample space and the space you are related to, the events you are interested in. So the probability of getting same coins, same side coin is 1, 2, and total number of sample space is 4. Therefore, 2 by 4 is half. Correct? That's how you generally compute the probability. Okay, so there are something else, another term which we'll use is called complementary events. Okay, complementary events are two mutually exclusive event whose which sum up to one. Okay, so for example, if I know the probability of of getting same side, uh, getting same face on the coin, then one minus that will be the other one. Because if if we are looking for these two, then these two means we are saying same face and different face, right? So same face and different face are kind of complementary events. All right, head and tail on a coin is a complementary event. All right. So those two events are generally called complementary events. If not this, then something else. Now, when we talk about complementary events, not all disjoint events are complementary events. Two events could be disjoint, but that does not mean that they are complementary event. There could be third event which is also disjoint from this. Maybe that is making up for the whole sample space. Okay. For example, getting getting one on the getting one on the dice is a disjoint from getting two, because getting one and getting two on the dice is totally disjoint, because one does not impact the two. So you cannot have a and b as in one and two, because that will be always zero. But getting one and getting two are not complementary events. Okay, but getting even and getting odd are. Okay, so everyone, what are the chances of getting an odd number while you throw a dice? What are the chances of getting an odd number? Question. What are the chances of getting odd number and odd number on a dice? Yes, Anusha? Yes, that's right. So that'll be so 2, 4, and 6 is even, while 1, 2, and 3. Okay. Now let me also talk about another question. Getting a number divisible by 4. Okay. So let's say probability of getting a number divisible by 4 is p. Okay. P. Now what will be the the probability of getting, I think this is fairly easy. So yes, I think that'll be simple. All right. So it'll be 1 by 2, and that's correct. So yes. Okay. So moving ahead. So two processes are independent. So we talked about complementary and disjoint. Disjoint means two things cannot occur at the same time. Okay. So the A and B is always 0. Okay, so two processes are independent if knowing the outcome of one provides no useful information about the outcome of another. For example, first coin toss had nothing to do with the second coin toss. You had when you did the first coin toss. You might have head or tail. Probability of both is same. Okay, but if you did a, picked up a card and you did not place the card back into the deck, the chances of getting A is changed, right? If you picked up a card from the deck and you did not put the card back, then the probability of getting A had changed, right? Probability of first A was 1 by 50, 51. Okay, while not 1 by 51, it was 4 by 51. The probability of this one was 4 by 51 because there are 4 A's in the deck, correct? Now when you did not put it back, the probability of getting A had changed, right? So the outcome of two draws from a deck without the replacement are dependent. So if this symbol, you see this symbol, it means probability of A when B has already occurred. This is what it means. PA by B, which means probability of happening A when B has already occurred is equal to A when A and B are completely independent. Okay, when both events A and B are already independent. Okay, in our previous example, if we have to write something like this, probability of getting a boy when we had a girl is zero point 0.5. Probability of getting a girl when we already had a boy is zero point 0.5. Probability of getting girl with already had girl is also zero point 0.5. Okay, so we always have the probability equal to the main one. Okay, so all right, so you can see that. All right, now moving ahead. So we have talked about it already. All right, next is the probability distribution. This is a very interesting aspect, the probability distribution. So you list down all possible outcome in the sample space, and then you list down the probability of every element in the sample space. For example, when you do the two tosses, what are the possible outcome? Head head, tail tail, head tail, tail head, right? The probability of each one is 0.25, 0.25, 0.25, 0.25. When you list down all of these things, all of these probabilities of all the elements in the sample space, we call it the probability distribution, the distribution of probability. Now, if all these events are disjoint, as in all these events are disjoint in the sense that head head and tail tail can never occur at the same time. Therefore, the total probability of okay, total probability will be 1. So this whole sample space will always result in 1 when the two things cannot occur at the same time. All right? When two events cannot occur at the same time. Okay? So whenever we are doing the probability distribution, we should keep in mind the event listed must be disjoint. Okay? So we generally draw the probability distribution on a curve. Okay? We generally draw a probability distribution on a curve. Okay, I think we have one good example of how we drew on the curve. Oh, I think that part is missing. All right. Oh, okay. All right. Okay, so let's just talk about the normal distribution. So most of the things in the universe, most of the aggregation or the counts follow a normal distribution way. Or let's talk about from here to here, how did we reach? All right, let's try to draw. If we draw a graph of the sum of the values on three dice throws. Okay. Okay, so I'll just say we are throwing, we are rolling three dices. We are rolling three dices. I don't know how it's called, dice or dice. Okay, we are rolling three dominoes or dice, having six numbers from 1 to 6. And then we are plotting the total versus the roll count. Okay, all right. So okay, total versus the okay roll count. Yeah, total versus the roll count. Okay, so if you roll three dice, what happens is, let's say total number of permutations. Who can tell me? The 1 2 3 1 2 3 4 5 6 1 2, or can I just try with two dice first and then increase it? So the total number will be 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, and so on. Okay, let me start R, and I hope I can find a way to do this. Okay, so there was a repeat, right? So we have dice, and we have 1, 2, 3, 4, 5, 6, and dice is a vector containing these numbers. And we could say, what did we do earlier to repeat these things? We did some sort of this. So there was a wave. How did we do this? I'm completely forgetting. So we had dice like this, and dice multiplied with dice. No, dice. Okay, no, not in this. Yes. Do you remember how did we multiply the that so many times? I think it was here somewhere. Yeah, 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 yeah. So, so this is what we did. So we are saying repeat each numbers. Okay, so what do we want to do exactly? We want to create a set of values where every number is being joined with every other number. And okay, I think it's easier to do for me and pen and paper. 1 plus 5, 1 plus 6. And then you have 2 plus 1, and so on. So this is how much? 2, 3, 4, 5, 6, and 7. Okay, so this is dice plus 1 is this much. So we can say our vector is dice plus 2, dice plus 3, dice plus 4, dice plus 5, and dice plus 6. So that is our number. So what is this? This is basically the total which could occur on the dice, right? This is the total which could occur on the dice. Now, basically we summed up the total, we threw the dice so many times. So 1, 1, 1, 2, all kind of possibilities. So the length of this one will be will be 36, right? 6 1, so all total possibilities, the full sample space is 36. Now this number which you see here, if you plot this quickly, you will see it has a behavior. If it has a behavior of the n- behavior of a normal graph. If you see that, even if you start from left to right, still you will see that there are on 2 how many numbers are there. Okay, so on 2 how many numbers are there? 1. Okay, on 2 there are only there is only one number, right? So if you are plotting here, This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 9, like that. So there is only one here. Okay. So at 2, there is only one number. At 3, there are how many numbers? Two numbers, right? Yes. So let me just shift it a bit. Okay, so either I remove this. Okay, so for 2 we have one number, for 3 we have two numbers, and for 4 we have three numbers, right? We have three numbers. For 5 we have how many? 4. We have one, 2, 3, 4. Correct? And now for 6 there are 5. For 7 there are 6. Correct? So the 6 could occur in many ways, right? So 6 is occurring 5 times. Okay. Fi 5 is occurring 4 times, right? 5 is occurring 4 times. Okay. 6 is occurring 5 times. 5 times as in there are there are 5 ways in which 6 can occur. Okay. Now, in how many ways 7 could occur? There are how many ways 7 could occur is there are many ways actually. Okay. So 7 could occur in many ways. If you sum up, basically what we have done is we made all possibility of throwing two dice together and summed up the numbers. And we draw the graph on the on x-axis we have the number, on y-axis how many times the total has occurred. So 7 has occurred 6 times. And then for 8, 9, 10, 11, 12, the same behavior as the other numbers will follow. Okay, so you will always get, in this case you will always get this kind of a curve, because there are only few numbers because of which a huge total will happen, like 12. 12 will happen only in the case when both the dice get 6 and 6, while 11 could happen when one gets 5, other gets 6, or one gets 6 and other get 5, right? While 10 could happen in three ways, while one get 5, other get 5, one get 4, other get 6, one get 6, other get 4, right? Similarly, so if you see this interesting pattern, so for 9 there are four numbers. The total 9 could occur when you have 3 and 6, 4 and 5, 5 and 4, and 6 and 3. So there are four possible ways. So when you draw this, you will see this interesting graph. This is normal distribution. We've already seen this kind of graph earlier when we were talking about the modality. Okay, the modality. These kind of graph, the normal distribution is a very natural form of graphs. Probably this is the most natural form of graphs. Okay, so if somebody gave you this distribution of numbers, and what you did was you all you did was did a histogram on this, and when you don't see there is a histogram of normal distribution, you will be quickly alarmed that there is something wrong in this computation. So the normal distribution in simple words says that the the rare things occur very less, meaning either the small number or the big number will happen very less frequently as compared to the average size numbers. Okay, or in another words, there'll be very few students in your class which will get high marks, very high marks, like 99 out of 100, and there'll be very few students in your class who will get very few marks, like 20 out of 100. But if in a class everybody's getting equal marks, there is something wrong. There is something wrong. There could be alarming. Maybe all the kids, maybe the exam was very simple, such that everybody was able to perform. Meaning, exam was superbly simple that everybody performed equally. Or there could be another case that the students were not taught at all and they were given a tough exam, so everybody scored almost zero. So in both the cases, raises the question on it raises the question on the level of examination. So if you plot a graph of the marks against total number of students getting that particular marks. So if you plot this graph, if you don't see a histogram of normal distribution, okay, some kind of a bell-shaped curve, some kind of a bell-shaped curve, if you don't see that, that means there's something seriously wrong. The process may be very artificial, or process may be not natural. So it's a very important phenomena to have such a graph. Okay, so do you want to take a 5 minutes break? Actually, I want to take a 5 minutes break. I completely forgot because I thought it's a 3 hours class. Okay, so we will continue with our normal distribution. This part is probably most important out of the whole thing. Okay, the reason why we learn probability, the reason why we try to plot it, this binomial distribution will help you doing the further analysis. Okay, all right, let's take a break for 5 minutes. Back by 9:26. All right, so should we start now? Yes, Anusha, should we start now? Are you back? Anusha and Sahab, are you back? Should we start now? All right, all right. Sahab is back. Anusha, are you there? Should we start now? All right, all right. Great. So we were talking about the normal distribution. Anusha? Okay. Yes. All right. So we were talking about the normal distribution. So what we demonstrated in the previous screen. So what we demonstrated in the previous screen is that if you try to compute the total number against the distribution, this is the distribution. When I say distribution, the occurrence of individual unique numbers and their frequency. For example, when we do the word count example in Hadoop, so each word is on x-axis and and on y-axis we have total number of word occurrences. Okay, all right. So so there will be always when you try to draw things, when you try to draw the distribution in a sample space, you will always get mostly the norm distribution, a distribution which will follow some kind of shape like this. So some people sat down and tried to figure out the graph, try to figure out the equation to represent this graph. One of the equations out of many equations, one of the equation is normal distribution. Although you can draw this kind of equation by using many other formulas, but normal distribution is accepted as one of the equations. So I think I have written the equation somewhere. Okay. We have very interesting discussion coming up. All right. So all right. So out of many distribution, there are at least 4 or 5 ways equations which you draw the equation, they come out like a bell curve. So a normal distribution is also one of those curves. Okay, so it's unimodal and symmetric. It's a bell curve. It follows very strict guidelines about how variability the data are distribution around the mean. Meaning the strict guidelines as in it's basically a mathematical equation which draws the whole curve. Okay, most of the variables are nearly normal, but no one exactly the normal. Okay, so this normal is basically one of the representations of the data. So earlier, this is a mathematical formula to draw this graph. Okay, and that graph can be drawn just based on two variables. If you know the mean and standard deviation, then you can draw this graph. Okay, it's as simple as that. So given to these two variables, you can draw this graph, and that is the quality of this equation, that it requires only these two variables. All right, so one is mean and other is standard deviation. Okay, so when your standard deviation is smaller, and when the standard deviation is smaller, the peak is very sharp, meaning the items are not much varying from the mean. Okay, so the position on the x-axis is decided by the mean, and position on the y-axis is decided by the standard deviation. The spread, basically spread is decided by the standard deviation. Okay, if your standard deviation is bigger, then the graph would look like this. Okay, or when the graph says this, it means the standard deviation is higher, meaning there are a lot of elements which are in different areas. Like if you think about a class having marks, so it shows that there are some people who have marks from 10 to 20 and 20 to 30, while in this case most of the students have the marks very close to zero. Okay, there are negative marking, there is a positive marking. So that's how the two graphs look like. Okay, now there are few important properties of this normal distribution. Normal distribution says that 68% of the data, 68% of the population is one standard deviation away from the midpoint. Okay, one standard deviation to the left, one standard deviation to the right, and you have 68% of the data. So so if you are given a mu and delta, okay, and so your kid comes up and says that, hey, I got 98% marks, right? So the next question you should ask is, what is the median in your class and what is the standard deviation in your class? And once you know that, you can clearly tell, what, you are not, you are in 68% student or 95% students. Okay, you can clearly tell them. So that's the quality of this graph. This graph, if you plot it, this is, some people computed this area under the graph, and then they found out that 68% of the area is under one standard deviation on both the side. Okay, on a spread of two standard deviation, 95% of the data is covered, and up to three standard deviation away from the mean, this area, as in from this point to this point, 98%, as in 99.7% of the data is between three standard deviation away. Now above, beyond this, there are only 2.3% people. Beyond this point, there are only 0.3% of the 2.3% of the people. Okay, out of the 2.3% people, 1.15% will be on the left hand side, 1.15% will be on the right hand side. Okay, so you can see that from, how much is this area then? If so Okay, so if you draw this, and you're already drawing it, how much is this area? This area is 34%. Okay, from this to this, I mean including under this curve, this will be 34%, and this much is, okay, this is half of 95%, and this is not this, this is from here to here, and here is half of 98%. Okay, basically 49% close to. Now, so basically, when you talk about normal distribution, you generally talk about this 68, 95, 98% rule. One standard deviation away from the mean, you are amongst 68% people. Okay, 68% of the people are covered in the one standard deviation norm. Meaning, if you know the standard deviation, you can easily tell. Uh, so, okay, so let me rephrase. Let me try to rephrase. What does it mean by 68%? That's what I'm trying to say. The population which is slightly varying from the mean, which is slightly varying from the mean. We will do the more computation, then you will know what does it mean. All right. So here is an interesting question to all of you, and these are the very common questions we see in daily life. A college admission officer wants to determine which of the two applicants scored better on their standardized test with respect to the other test takers. Okay, so Pam, who has got 1800 on her set. So Pam appeared for set and Jim appeared for ACT. Okay, Jim got 24 marks in his ACT and Pam got 1800 marks on her set. Now, out of Jim and Pam, who looks smarter to you? So, your next question will be, what is the mean? What's the average marks people generally get in SAT or ACT? Now, let's say you only know mean. Somebody said 1500. And so let's say SAT has mean as 1500 and ACT as in ACT has mean as 21. Okay, now if you don't know the standard deviation, what will you do? You will say, okay, so the mean is 21 and he scored 24. Okay, so he is 3 away from the mean, which means 3 divided by 21. Okay, and mean is 15 and he is uh, 300 better than 15. So he is 3 out of 50. She's 3 out of 15. Now, does that mean anything? So I mean, this is a standard question. If you know about the Indian CBSE and ICSE, so unless you know the standard deviation, you cannot judge. You cannot judge just based on mean. Okay, so what you will do is you will try to find out how far are they, in what percentile of the people are they in. Okay, so what will you do is you will draw it on the graph and you will find out in what percentage of the people are they in. Okay, so how many standard deviation is C away from the mean? Let's just compute it. Okay, the standard deviation is 300, and how many standard deviations is away? So what we'll do is 1800 divided by 1500. This much sees away from the mean, which is 300 marks sees away from the mean. Okay, now what is the standard deviation? On an average, how people are varying in this crowd. Okay, so we divide by that is standard deviation, so we get 1. Okay, now Now let's do the same thing for Jim. Okay. Now let's do the same thing for Jim, which means what was the number? So he got 24. 24 minus 21, that is 3, divided by standard deviation is 5. So he is hardly zero point 0.6 away from the standard deviation. Okay, so on this curve, he is zero point 0.6 deviation, as in somewhere here, while she is here. which means C is a brighter student. Correct? All right. So, what is your opinion out of Pam and Jim? Who is brighter student? Who got better marks? So generally, we shrug off saying that we are trying to compare apples and oranges, but it is actually comparable. Yes, Anusha and Sahib, what is your opinion out of Jim and Pam? Which one do you think is a brighter candidate? All right. So Sahib is agreeing with me. So okay. Now my question to you is: had Jim's marks been, say, okay, 26. Okay. So had Jim scored 26, then who is smarter, Jim or Pam? In your opinion, who is better amongst Jim and Pam? Okay. So question is, let me just change the question a bit. What if this could have been the case? Okay. So let's say, let me just rephrase. So let's say Pam, who earned 1800 on her SAT, or Jim, who scored 27 on his ACT. And these are the detail about SAT. Okay. So Sahib, how are you computing this? How many standard deviation is Jim away from mean? No, the mean is still 21, not 24. Yeah. That's right. So we will subtract. Good, good. All right, good, very good. All right. Now, this is how it looks on the graph. When you have 24x as marks, the way you compute is this is called Z score, Z score, we call it. So basically, all you do is you try to find out how much this person is away from the mean. How many standard deviation is this person away from the mean? Okay, so you need mean, you need standard deviation, and that's it. Okay. All right. So the other exercise, one is that given these values, you have to find out who is better. So for that, you do the Z score. Z score means observation minus mean divided by standard deviation. Okay. Or you could say standardized score. We call it G score or standardized score. Of an observation is the number of standard deviation it falls above or below the mean, which means z-score of a mean is 0. An unusual observation generally falls under g greater than 2. Okay? If somebody is more than 2 deviation away from the mean, then it is definitely an outlier. Because as we talked about earlier, beyond 2 deviation away, beyond 2 deviation away from here means being in this section, being in this section, which is hardly 5%. Okay, this is 2.5%, this is 2.5, because up to 2 standard deviation everything is covered. If you do the integration or if you try to compute the volume under this 2 deviation away from this point, then you will have the you will find out that it's 95% of the people are under the crowd up to the second deviation. Beyond second deviation is an outlier. Okay, so what you do is given an observation, find out how is that observation varying against the mean in terms of standard deviation. You find out the standardized score or z score of an observation, and then if it is falling beyond, if it is coming out to beyond 2, then that person is definitely an outlier. Now question to you is on what score of on what score we will call Pam outlier? On what score, what marks we will call Pam, what do you call, unusual? Okay, unusual. On what marks, how many marks should Pam get so that we call Pam outstanding or unusual? We are talking about Pam, not Jim. All right, that's correct. Greater than 2100. Why? Because we are saying greater than 2 standard deviation, which is 600. If it is 600, more than 600 above the mean, that means a person is an outlier. Okay? All right. So whenever, yes, that's correct, Anusha. Brilliant. Brilliant. Or It could be, in case of outlier, we could also say less than 900. That's brilliant, Sahib. Good, good. So everybody is with me. All right. Now, so the good news is that earlier times when there was no computer and the we had to compute the percentiles. Okay. All right. So this is G score. We talked about G score. We talked about standard deviation. We talked about mean. Okay. And we also talked about something here. We talked about percentages of people under the graph. Okay. So percentage of people under the graph is also called percentile. Okay. Percentile. Percentile is you convert the percentages into zero, between 0 to 1, meaning divide by 100. That's called percentile. All right. Now, G score can be used to compute percentile of the people, meaning there will be there will be maximum number of people. So half of the people will be up to a percentile of the mean. Sorry. Okay. Let me try to say something else. Okay. So given an standard deviation and given a G score, you can standard deviation, mean, and something called Z score. You could always compute the percentile. It's like saying that okay, my marks are these. Given one person's marks, we can compute the Z score, and based on this Z score, we can compute the area of the curve up to that point. Okay, meaning, and then we can, so there are, earlier there used to be a chart between which will draw a graph between the z score and the percentile. Okay. There used to be these charts like logarithmic tables. Similar to that, we used to have the normal distribution tables in which they will list down the z-score and against the percentile. Okay, so given a percentile, you could figure out how much z-score it has got, and given a z-score, you could always compute the percentile. So whenever somebody comes to you and say, hey, I got these many marks, okay, and the next question you ask is, can you tell me what is the standard deviation and mean, so that I can tell you how many, amongst how many percentile of people are you in? Okay, amongst how many percent of the percentile of the people lying below you. Okay, so at any point of time we can do that computation based on the chart. Now the same thing has been fed into a library in R, so that you could quickly compute this percentile. For example, this p norm is that one. Okay, if somebody comes to you and says that, hey, I got -1 marks, okay, and the mean is this, standard deviation is this, you will quickly be able to tell the percentage of the people who are below him. Okay, who are below him. All right. So is this clear? So graphically, percentile is the percentage of observation that fall below a given point. Okay, graphically, percentile is the area below the probability distribution to the left of observation. So when somebody comes to you and tells you marks, you'll tell that okay, you are, these many percentile of the people are below you, and these many percentage of the people are above. So percentile means this left hand side area, these many people. Area represents total number of people, because at every observation there are number of people for every observation. So if you sum up all of that, then you will get this volume representing total number of people up to this point. Okay, so under the curve, this whole, under the curve, if you count, if you take a scale and or try to compute the total number of bars, as in you split this curve into very small strips and then sum it up, then you will get the total, you know, the total number of total number of people. And by the way, if you have forgotten, let me just remind a quick thing. So the way we compute the area of such big curve where it's very difficult, let's say this curve is there. So what we do is we generally draw bars like this. Okay, we generally draw bars like this, and then we ignore we ignore this part, this one which is not there, and yeah, we generally ignore this part and just sum up this, and so on. Okay, so summing up the heights of the total number of people at every value will give us the total values. That's what this integration or summation will tell you. All right, so p norm is nothing but given a value of x, find the integration of this area, find the area, find the total area here. Okay, and since this gives you this number, it's basically divided by total population. Okay, it'll be always 0 to 1. All right, now next question to you, all of you, is the set score are distributed normally. Also, whenever you're doing the computation, you need to know that you can only apply normal distribution only if the problem statement says so, or somebody explicitly, or it is your assumption that this is normal distribution. Not every graph is exactly normal, and most of the graphs are mostly normal. Okay, they're closer to normal, not really exactly normal, because normal is basically few people studied and they found out, okay, this graph is something that fits to most of the situations. All right, so set scores are distributed normally, which means 1500 is the mean and standard deviation is 300. Okay, Pam got 800 on SAT. What is the percentile score? Meaning, how many percentile of the people C is better than? Okay, so how do you compute? We are given mean of 1500, we are given standard deviation of 300, so z score is 1, right? So we say p norm, we say 1, and what is the mean? Mean is 1500, and standard deviation, so we have to pass it with the standard deviation is 300. Okay, so this looks awkward. Alright, so P norm does not require Z score. Okay, let me just see. Help P norm. Oh, there's no help actually for P norm. Alright, so for P norm, we give the actual value, not the Z score. That was a mistake on my part. So given a value, actual value, you can do the computation. You don't need to compute the Z score. So it gives us there are 0.84 out of 1.84, meaning there are 84. C is better than 84.13 percentage of people. C is better than these many people. Okay, which means she will be lying somewhere this side. All right. Now a friend of yours tells you that C scored in top 10% on the set, SAT. What is the lowest possible score she could get? Meaning, she comes to you and says that the score she has got is in top 10% of the people, which means her percentile is zero point 0.9, right? Her percentile is zero point 0.9. What is the score? And the mean and standard deviation is, so let's assume for time being. So she's saying that she's amongst top 10%, right? So her score would be little better than 1800. So we say 1900. Mean is 1500 and standard deviation is 300. How much is it? Oh, we are very close, little bigger than this. Okay, so we could say 1450. Oh, that's still, how come? Okay, sorry, we are changing the mean, not the actual value. So we are saying 1890. Oh, it did not change much. 1800 is okay. 1850, 1870. Okay, we are going closer. And 1878. Alright, so we are doing a hit and trial, right? Instead of doing a hit and trial, if we use the formula for, if we use the formula for, say, formula for this, which is Q norm. So Q norm accepts the percentile, which is zero point 0.9, and mean equals to 1500. Standard deviation equals to this. So we'll get exact number. Okay. So you could see that we were also doing very closer to this one. Okay. So instead of doing the hit and trial, you could use Q norm to do the reverse of what this guy did. So given an observation, finding out how many percentile of the population is below this particular number is done using P norm, and how many, if you want to do the reverse, okay, if you want to do the reverse, that how many percentile of the people, given a percentile of the people, you have to find out the marks, then you can use this formula. All right. What? All right. So I did not get your question, Sahib. So should I mute you for a second? All right. All right. So that's pretty much for today. Let me stop the recording.